Hello and welcome to this new video. In this video, I'm going to prove three results about homogeneous Markov chains that follow from the definition. The first result concerns the computation of some probabilities related to Markov chains. So suppose that we have a homogeneous Markov chain Xn with initial distribution given and a transition matrix Pij. Then, for any sequence A0, A1, An of states, we can compute the probability of this event, x0 equal A0, x1 equal A1, x1 and An. So this is what we call actually a path. Okay, it's a path of the Markov chain. How can we compute this probability? We we follow a multiplication rule. So we multiply the initial distribution at A0. Okay, so which is just P of x0 equal A0, the first probability, times the transition probabilities from A0 to A1, from A1 to A2, and etc. up to An minus 1 An. So it's very easy, and you shall see examples. And we can also compute the conditional probability of a path, given that we start from A0. Okay, so just the same thing. Okay, so why this is true? This is just a consequence of the multiplication rule that you probably learned in probability theory. So if you have a sequence of events, E0, E1, En, then the probability of their intersection, this is just the notation of the intersection that is useful in probability. So it takes less place, actually. So this is the probability of the event E0 and E1 and E2 and En. The multiplication rule states that the probability of the intersection is the product of the probability of the first event times the conditional probability of the second event given the first times the probability of the third event given the intersection of the first two, and so on. Okay, we can also write it in reverse order actually. So now I'm going to apply this for the events E0 is the event x0 equal A0, E1 is the event x1 equal A1, and so on. Okay, actually you can, if you don't remember that, you can prove it by induction, right? Actually for n equal 1, this is just the definition of a conditional probability. So if n equal 1, the probability of the intersection of 0 times E1, of E0 and E1 is the product of the probability of 0 times the conditional probability of E1 given E0. Okay, and this is the definition of the conditional probability. Okay, so the probability now of this path, x0 equal A0, x1 equal A1, up to xn equal An, is, so you apply this formula, and you get that, right? And now we are almost done, because now we apply the Markov property. So the first term I don't change. It's just alpha 0 A0. The second probability is precisely the transition probability from A1 to A2. Sorry, this is A0 actually. So A0 to A1. There's an error here. And now if you look at the third term, Px2 equal A2, given x0 equal A0 and x1 equal A1, the Markov property tells me that I can eliminate the x0 condition. So this is the past, present, future. And same thing for the last term, we can eliminate everything up to xn minus 1. And that's it. So we get precisely the transition probabilities that I'm talking about. Okay, so this is this illustrates the use of the Markov property in practice. Okay, and that's it. Now, property B actually follows from A and the definition of conditional probability, because this conditional probability is the probability of the whole intersection divided by the probability of x0 equal A0, which is just this one. Okay, so it's very easy. So now we can compute probability, conditional and unconditional probabilities of paths of a Markov chains, of the Markov chain. Okay, this is easy. Now, the second result, so let us illustrate this on an example first. So consider the simple weather forecasting model that we introduced in the first video. Okay, so we have two states, rainy, not rainy, and we have this transition probability matrix. And suppose now that we have an initial distribution, so the probability that it's rainy initially is 10% and not rainy 90%. First question, we would like to take a 3-day vacation, and you ask what is the probability that it does not rain during these 3 consecutive days. Okay, so we start day 0. So actually it's not rainy, so rainy is state 0, not rainy is state 1. So we need to compute the probability of this path, not rainy today, not rainy tomorrow, not rainy the 3rd day, right? Now, of course, by homogeneity, we can also, this is also the probability of x1 equal 1, x2 equal 2, x3 equal 1. So 1, 1, 1, because it's homogeneous. So according to the rule of the previous proposition, we have to multiply so it's the product of 3 things: the initial distribution at 1, and the transition probability from 1 to 1 times the transition probability from 1 to 1 as well. So we get this formula. And just replace now. Alpha 0 of 1 is 0.9. P11, this is P11 because this is P00, P01, P10, and P11. So P11 is 0.6. And so we have 32.4% actually of not raining during 3 consecutive days. Okay, now another question illustrating the point B. Given that it does not rain today, what is the probability that it does not rain the next 2 days? So this is a conditional probability. Okay, it's the conditional probability of the path x1 equal 1, x2 equal 1. So we just have, once again, P11, P11, and it's 36%. Okay. Now, remark, as I think I already pointed out this remark. So the probability transition matrix of a homogeneous Markov chain is what we call a stochastic matrix. A stochastic matrix is just a matrix, square, it should be square actually, such that each entry is between 0 and 1, or you can just put positive here, and each row sums to 1. We don't need this condition. Actually, it's redundant, because if all terms are positive and they sum to 1, so all of them are less or equal than 1. Okay? So we know that because these are probabilities, actually, a probability transition matrix is of a Markov chain is a stochastic. But you shall see the converse also as well, that every stochastic matrix is the transition matrix of some Markov chain. This would be the 3rd result of this video. Okay, so we can characterize the Markov chains by their transition probability matrix. And as a first exercise to test your understanding, prove that any power of a stochastic matrix is also a stochastic matrix. This is just a useful exercise in induction. Just use induction. And please do it, because next time we shall use ideas involved in this exercise. Okay. Now, next result is a reformulation of the property that the probability of the future given the past and the present is equal to the condition probability of the future given the present. In the definition, actually, you just took the future to be xn plus 1, right? But we can prove a more general property, if you like. We can actually, instead of saying that the future just xn plus 1 equal an plus 1, actually the future could be any set of this event. Okay? And so n is arbitrary and k is arbitrary. And instead of the past taking, instead of taking the past to be x0 equal a0, etc., could be any subset of this. And the present usually is just one instant. So then the result states that the probability of the future given past and present or present and past, is the probability of future given present. Of course, provided we don't divide by 0. Okay, so note that this result looks really like the definition, but now it's a little bit more general. So we don't need to consider just the future to be x at n plus 1. Okay, it could be any sequence in the future, right? So now we could have given this as a definition actually of a Markov chain. But this is not so convenient, because if you want to prove that rigorously by going back to the definition that a process is a Markov chain, we don't need to verify or to check this condition at each time. It's enough to check the definition. And I'll give examples later, actually. Sometimes I may ask you to prove by going back to the definition that some process is a Markov chain or a homogeneous Markov chain. Okay, I ask such questions in the exam. So this is why we need a definition, because when we have a definition, we can prove theorems. Okay, so if you prove that a process is a Markov chain according to our definition of last video, then this property is automatically satisfied, which seems to be more general, but actually it follows from the definition. Okay, so let us prove it. It's enough to prove it actually for B equal this and F equal this event, right? Because the general rule, as we shall learn later, will follow from this. But we have to use what we call the total conditional probability formula that I will explain in the next video. Okay, already it's interesting to prove this when B is exactly this event and F is exactly this event. Okay, which is not something that we formulated in the definition. Okay, but this is something that we can deduce from the definition. Okay, so let us see. We use the multiplication rule, but in reverse order. So the probability of future, present, past, right? So A is the present. So future, present, past is the probability of this path. x0 given, x1 given, etc., xn given, xn plus 1 up to xn plus k. Okay, now this is the intersection, the probability of an intersection of an event. So if we write the multiplication rule in reverse order, so we start with the last event given the previous, the probability of this could be en minus 1 actually given the previous, and so on. But we start at the probability of this is E0 actually, right? So, and now we apply the Markov property, which tells me that I can, when I have a conditional probability given the present, I can neglect everything before. So the probability that xn plus k equal an plus k, given what is before, I can eliminate everything here. So the first probability, the first term here, is the probability of xn plus 1 equal an plus 1, given just xn equal an. So the first term is just equal to p of xn plus k equal an plus k given the previous event. So I can eliminate everything before. Same thing for the second term, etc., up to the last term. The last term is just the probability of the present and the past. Okay? Now, in a similar way, if I just use, if I just compute the probability of the future and the present, okay, so same thing. We write the multiplication rule in reverse order. So it's p of xn plus k equal an plus k given the previous event times the previous event given the previous event, and so on, up to the last one, which is actually p of xn equal an. This is just the present. So same thing. Okay, so the same argument works here. Okay. So how can we reformulate these two facts? So p of future, present, past is equal to some number times probability of AB. So this product up to PA plus B, I call it X. So I can write P of FAB is X times PAB. Okay. So everything before I call it x, and then in the second equation, everything before PA I call it x because it's the same x. Okay, so what is x? X is the number between 0 and 1, which is the probability of xn plus k equal n plus k given the previous event times etc. Up to the probability of xn plus 1 equal an plus 1 given xn equal an. Okay, and now we are almost done because now we have, since probability of AB is positive, then the probability of A is positive. So from the one hand, we have x equal P of F AB over PAB. And the second equation gives me that x is equal PFA over PA. Now the ratio, this is just by definition, P of FAB over PAB is just the conditional probability of F given AB. And the second ratio is just the conditional probability of F given A. Okay, so we have proved, therefore, a more general property, another interpretation of the property that probability of the future given past and present is just equal to probability of the future given the present. Okay, we had to prove that because it was not written as it is in the definition. Okay, but we could deduce it from the definition. Okay, so we shall use this important property in the sequel. Okay, last result, a deeper property of Markov chains. Another look, it gives us another look to Markov chains. So consider a finite set S, which is to be the state space, and consider an arbitrary set, could be 0, 1, that we call A. If you have any function of two variables from S times A into S, so we don't assume anything actually here, any regularity, just to be any function, because our sets are finite. Okay, so measurability, if you like, is just something trivial. And suppose that we have an IID sequence Yn, right? That takes values in A. Okay, for example, think of A to be 0, 1 and Yn to be uniformly distributed on 0, 1. And moreover, consider an initial random variable taking values in S, and which is independent of Yn. There's an error. Then we construct by induction the following sequence. We start from x0, and then we put x1 equal f of x0 and y1. Okay, it's perfectly defined actually now. And then we reiterate this process with x0 replaced by x1 and choose another independent from the previous one. Okay. Then we claim that this, so we have now a discrete process defined in this way, and we claim that it's a homogeneous Markov chain, first thing. And by the way, this is what we call a discrete random dynamical system. A dynamical system is actually, a discrete dynamical system is just an iteration of a function. So a deterministic discrete dynamic system is just something of the form xn plus 1 equal f of xn. And we saw something similar in chapter 0. Now here we have a random term, right? So this is why it's called a discrete random dynamical system. And the converse is true as well, in the sense that for a homogeneous, if you have a homogeneous Markov chain, then there exists another Markov chain given by 1 and having the same distribution. Okay, so we can think of a Markov chain as a random dynamical system. So this equation can be written as, because it's an iteration rule, so new state equal f of the old states plus noise. In deterministic mechanical system, you had something like new state equal f of the old state, but here we have noise, so this makes it random. Okay, now why this is true? Okay, so first let us prove by going back to the definition that the sequence given by 1 satisfies the Markov property according to our definition. So instead of checking proposition 1.2, just check the definition, and this is easier. So just go back to the definition and we compute the probability of the future given present and past. We just replace. Xn plus 1 is by definition f of xn and yn plus 1. right? So just replace. And now, since we are given that xn equal I, we can replace xn by I. So we get the third equation. So the probability of this event, this conditional probability, is the probability that f of I yn plus 1 equal j, given the previous history. Okay, now the random variables x0, x1 up to xn are defined in terms of themselves and the independent random variables y1 to yn. And I assumed in the assumption that the sequence y0, y1, yn are actually independent. So any subset, so y in particular y1, y2, yn is independent of yn plus 1. So therefore, any function of y1, yn is independent of any function of yn plus 1. This is something that you prove in probability. So this event actually is a function of y1, yn, and this is a function of yn plus 1. Okay, by independence, okay, this event here is independent of this event. Okay, and therefore this is just, I can eliminate everything before, even the present. So the probability that I'm searching for is just P of f of I yn plus 1 equal j, right? And also, well, I can also, since xn is independent of yn plus 1, so I can also write it as a conditional probability. This changes nothing. And I can write this event now as P of f of xn yn plus 1 equal j, given that xn equal I. And now this is just xn plus 1. So I get P of xn plus 1 equal j, given that xn equal I. So in summary, we proved that P of the future given present and past is equal to probability of the future given just the present. And so we have proved by going back to the definition that our discrete random dynamical system satisfies the definition of a Markov chain, and therefore it's a Markov chain. Okay. Now the converse is more interesting. So since S is finite, we can call it 0, 1L. And suppose that Xn is a homogeneous Markov chain on S with the initial distribution given and the transition probability matrix. Okay. I would like, what do I have to prove? I have to find a discrete dynamical system which has the same distribution as Xn, right? Okay. Now, this is one of the rare places where we use measure theory, but in a simple setting. So we consider the set 0, 1 equipped with its Borel sigma algebra and the Lebesgue measure. Okay, I don't need the Lebesgue sigma measure, just Borel is enough. And so you know what this is. Lambda is just lambda of an interval, just the length of an interval. Okay, and this is the fundamental property of the Lebesgue measure. Okay, this is all I need to know. That the Lebesgue measure gives a meaning to the notion of length for subsets which are not really intervals, could be anything actually. Okay, and consider now an IID sequence Yn, which is uniformly distributed on 0, 1. Okay, and now let us construct our dynamical system. Okay, define a random variable W0 in this way, sigma from k to L of k1 ak, where ak is given by this event on this probability space. So this is just a Borel set. Now, what does this mean? Don't be afraid of the notation. This means that W0 takes, what are the values taken by W0? They are just 0, 1, 2 up to L, because they are just k times a characteristic function, which takes just values, two values, 0 and 1. So the values taken by W0 are just k from 0 to L. Now, with which probability? With the probability is given by the probability of ak, which is just lambda here in this case. So lambda is just the length of this interval. And since y0 is uniformly distributed, okay, these quantities are just sigma of this minus this, okay? where the alpha I are the initial distribution. So these are numbers between 0 and 1. So, right, so by definition of a uniform random variable, the probability of AK, or lambda of AK in this case, is just the length of the interval. So it's just actually alpha K. And now we proceed by, now we define our function of two variables, function of the state and the noise. So same thing. So FIT takes values from 0 to L, same thing. But now instead of the characteristic function of AK, I take the characteristic function of BIK of T, which now depends on three variables. T is just a real number actually here. And BIK is this interval. Okay, so this is just actually a deterministic function now. Okay, this is the kind of functions that we study in measure theory. Okay, it's what we call a simple function. And so we can, okay, so FIT takes the values 0 in L, provided T is in this interval. Okay, so this is a deterministic function, and now we define our dynamical system in this way. So Wn plus 1 is f of Wn and the noise. Okay, so f is here deterministic, Yn is random, and therefore, since W0 is random, so we start with the random. Could be constant, actually, no problem, but the noise is in the second factor. Okay, so new state equal f of old state and noise. Okay, and this is what I was trying to explain. So the second equation, this is what we shall now apply. So FIT takes the value j. J is anything from 0 to L. When does FIT equal j? Precisely when T is in Bij, right? Because it's a characteristic function. So when FIT equal j, this means that this number should be equal to 1, right? And so this is what I wrote here. So FIT equal j exactly, or if and only if T belongs to Bij, right? And now we are almost done. So now the probability of Wn plus 1 equal j, given that Wn equal I, just I replace Wn plus 1 by its value. And now this conditional probability, actually, I can replace Wn by its value because it's conditional probability. And so since Wn and Yn plus 1 are independent, any function of Wn is independent on any function of Wn plus 1, of the Yn plus 1. So I can eliminate this, right, by independence. And now I just replace f of I Yn plus 1 by its value. This is just the definition. Okay, and so now, okay, when does this event happens actually? By the remark before, this happens if and only if Yn plus 1 belongs to Bij, right? And we are almost done because this is uniform and Bij is a subset of 0, 1 by definition. So by definition of a uniform random variable, this is just the length of Bij, okay, or the probability that I'm considering. But the length of Bij is just Bij, right? Because this is an interval. So this is this sum minus this sum. So this is just Pik actually. So Bik is Pik. So Bij is Bij, right? And that's it. So we proved what? Actually, we know that Wn, by the first part, we know that Wn is a homogeneous Markov chain. But what we proved is that the transition probability is exactly equal to Pij. So what did we prove actually? We proved that, so we started with a Markov chain with initial distribution and the transition probability, and we constructed another Markov chain, which is a dynamical system, and the two actually have the same transition probability, and by our previous result means that they have the same distribution. Okay. So the argument that we used actually, so let's finish the proof. The argument that we used actually proves that any stochastic matrix is the transition matrix of a homogeneous Markov chain that you construct in this way. Okay, so this is actually, you can consider this as an existence theorem, because systems of this form always exist, right? By induction, you start from W0 and you iterate. Okay, so it's an existence theorem actually. So now we have, to summarize, we have three ways to look at Markov chains. The first intuitive point of view that we started with by talking about snake ladder. It's just an object. A Markov chain is just an object moving between states with certain transition probabilities. Okay, and this point of view is very important actually, because this is the point of view that permits modeling of a situation as a Markov chain. Okay, this is the easiest way to think of Markov chains, and it's very simple. Okay, so don't be afraid of the machinery that we are trying to develop. Okay, so basically it's something very simple. The second property that we explained in the previous video is the Markov property that we can replace in several ways, but it says that the probability of the future given past and present is equal to the probability of the future given the present. Okay, and now we have at least two ways of writing this equation mathematically. The definition and proposition, the second proposition of this video. Okay, and now we have a third point of view, is that we think of a Markov chain as a discrete random dynamical system, right? But it's not really a discrete, but it is equal in distribution to a discrete random dynamical system. But in probability, the nature of the random variable or the process is not really important. What is really important in computation is the distribution. Okay. So we can, if you have a Markov chain, you can replace it by a discrete random dynamical system. Okay, and you don't change anything. Okay. Now, what about non-homogeneous chains? A non-homogeneous Markov chains also can be thought of as but time-dependent dynamical systems. So instead of having one fixed rule f, we have at each step a new rule. Okay, so if you like, this is a function of xn, yn plus 1, and n. Okay, so we have now three variables. So we have old state, noise, and time. Okay. And now I will leave you with two exercises that, so I would really appreciate if you can solve them on your own. Okay. These are meant to test your understanding. So second exercise in this video, give an example of a discrete state process which is not a Markov chain. It's very important because not everything is a Markov chain. But so I want you, according to what we said so far, to come up with a very simple process. It should be discrete time and discrete state. It's not necessarily finite. It could be infinite. It's not really a big problem. So come up with a very simple process which is not a Markov chain. Okay. And second exercise, show by a counterexample that the Markov property does not mean that P of the future given the past is equal to P of the future. Okay, this is usually a stronger assumption. Okay, here it means that the future is independent on the past, but this is not what the Markov property states. The Markov property, so it's very important actually, it's the future depends on the past, but only through the present. Okay, so these are two completely distinct properties. Okay, so this concludes the second video, and so we are done with the first section 1.1. Next video we are going to deal with section 1.2 about the Kolmogorov-Chapman equations, which are very important in computations. Okay, so thank you for your attention.